A vehicle bus is a specialized internal communications network that interconnects components inside a vehicle. Special requirements for vehicle controls such as assurance of message delivery, of non-conflicting messages, of minimum time of delivery, of low cost, and of EMF noise resilience, as well as redundant routing and other characteristics mandate the use of less common networking protocols. Protocols include Controller Area Network, Local Interconnect Network and others. Conventional computer networking technologies are rarely used, except in aircraft, where implementations of the ARINC 664 such as the Avionics Full-Duplex Switched Ethernet are used. Aircraft that use AFDX include the B787, the A400M and the A380. All cars sold in the United States since 1996 are required to have an on-board diagnostics connector, for access to the car's electronic controllers. Background: the main driving forces for the development of vehicle network technology have been the advances made in the electronics industry in general and government regulations imposed, especially in the United States, in order to make the automobiles environmentally friendly. With stringent limitations placed on the emission gases for the automobiles, it became impossible to retain this level of control without the help of onboard computing devices. Onboard electronic devices have also contributed substantially to vehicle performance, occupant comfort, ease of manufacture and cost-effectiveness. At one time, a radio was likely the only electronic device in an automobile, but now almost every component of the vehicle has some electronic feature. As mentioned above, some of the typical electronic modules on today's vehicles are the engine control unit, the transmission control unit, the anti-lock braking system and body control modules. An electronic control module typically gets its input from sensors that it uses in its computation. Various actuators are used to enforce the actions determined by the module. The modules need to exchange data among themselves during the normal operation of the vehicle. For example, the engine needs to tell the transmission what the engine speed is, and the transmission needs to tell other modules when a gear shift occurs. This need to exchange data quickly and reliably led to the development of the vehicle network. The vehicle network is the medium of data exchange. The automotive industry quickly realized the complexity of wiring each module to every other module. Such a wiring design would not only be complex, it would have to be altered depending on which modules were included in the specific vehicle. For example, a car without the anti-lock brake module would have to be wired differently than one that included anti-lock brakes. The industry's answer to this problem was to create a central network in the vehicle. Modules could be plugged into the network and would be able to communicate with any other module that was installed on the network. This design was easier to manufacture, easier to maintain and provided the flexibility to add and remove options without affecting the entire vehicle's wiring architecture. Each module, a node on the vehicle network, controls specific components related to its function and communicates with the other modules as necessary, using a standard protocol, over the vehicle network. Networks were not new, but their application to the vehicle was. The networks for the vehicles called for low cost, immunity from external noise, ability to operate in harsh environments, overall robustness and reliability. Although the vehicle network did not place too much emphasis on the data throughput, the demand for more onboard computing is continuing to drive changes to these networks to provide higher speed communication between modules. The control area network include the receiver and transmitter for the host-to-controller transmission and interlinking between the computers. Protocols, physical media and connectors. There are several network types and protocols used in vehicles by various manufacturers. Many companies are encouraging a standard communication protocol, but one has not been settled on. Protocols. Common vehicle buses protocols include ARINC 429, Betaflight, CAN an inexpensive low-speed serial bus for interconnecting automotive components, D2B a high-speed multimedia interface, FlexRay a general-purpose high-speed protocol with safety-critical features, DC Bus, 1, a automotive power line communication multiplexed network, IDB 1394, IABUS, EA2C, ISO 9141-1/2, J1708 and J1587, J1850, J1939 and ISO 11783 an adaptation of CAN for commercial and agricultural vehicles, keyword protocol 2000 a protocol for automotive diagnostic devices, LIN a very low-cost in-vehicle sub-network, MOST a high-speed multimedia interface, multifunction vehicle bus a part of the train communication network IEC 61375. SmartWire X, SPI, VAN a equals physical transmission media equals, some examples of physical transmission media use in vehicle networks, single wire, twisted pair, fiber optic, IEEE 1394, MILSTD 1553, developed for use in military avionics, it is now widely used in spacecraft too. Adopted for the MiG-35. MILSTD 1773, roughly MILSTD 1553 with optic cabling, power line communication, 2. Connectors equals, OBD2, additionally, many major car manufacturers use their own proprietary vehicle bus standards, or overlay proprietary messages over open protocols such as CAN. Protocols usage. Early history of buses on GM vehicles. The earliest known GM data communication link from one electronic module to another was introduced in the 1980 model year Cadillacs. The link was one wire point-to-point, linking the engine control module to the fuel data panel. In model year 1981 all GM passenger cars for the U.S. market used a similar data link to a test connector for assembly line diagnostics. The value of this data in diagnosing emission systems after customer delivery was quickly identified. Scanner tools were made to view and interpret the data stream. The data line was the same line that turned on the check engine lamp in the instrument panel. Data was sent at 80 bits per sec 9 bits per frame, 21 bytes, 2.4 seconds transmission. In 1981 model year Cadillacs, two 80-bit point-to-point links were present, with the second link going from the engine control module to the climate control module. In the 1982 model year, fuel injection engine control modules at the data port moved to a dedicated full-time connection. In the 1983 model year, the data rate on the fuel injection engine control modules was doubled to 160-bit S. In the 1984 model year, Corvette instrument panel used data from the fuel injection engine control module's data link. In the 1985 model year, Cadillac FWD-C vehicle had an electronic system that has point-to-point data links between 5 electronic modules and a dedicated assembly line diagnostic connector. On the 1988 and 1989 model year Buick Reatta and 1986 1989 model year Buick Riviera touchscreen CRT-equipped vehicles, an 8192-bit S data bus was implemented between the body computer module and the assembly line connector, climate control module, and CRT controller. This was GM's first multi-drop data bus. All GM vehicles adopted this bus as new engine control modules were developed. This bus remained the standard GM vehicle bus until 1996 when the J1850 VPW bus replaced it. References: The Electric Jet. Phillips, E.H. Aviation Week and Space Technology February 5, 2007. http www.Defense Update CMIG 35 HTM, Ronald W. Cox, Local Area Network Technology Applied to Automotive Electronics Communications, IEEE Transactions on Industrial Electronics, Vol. IE 32, No. 4, November 1985, page 327 to 333.